Okay, when you're provided with a equilibrium constant K and also starting concentrations for a reaction, you can determine what the equilibrium concentrations are. And we call that type of problem an ICE problem. You can see that's an acronym, and we'll talk about what that means in a second. So for example, if we're given this equation down here, 2NoCl goes to 2No plus Cl2. And because it's an equilibrium problem, I'm going to try and get better at making sure I've got my double-headed arrows on everything, because this is an expression that comes to equilibrium. We're given a K of 1.6 times 10 to the negative sixth. Sorry, I changed that last minute. The first thing we're going to do in any sort of equilibrium problem often is just write out the equilibrium expression. And I do kind of want to talk about what it means that 1.6 times 10 to the negative sixth is the equilibrium expression. So the equilibrium expression here is going to be, remember, reactants over products, even though I said that wrong the one time. Oh my gosh, I just said it wrong again. That's products. I'm writing it right. Okay, NOCl squared. Okay, so that's the equilibrium expression for this reaction, and it's 1.6 times 10 to the negative sixth. That negative sixth means that we must have a large denominator compared to the numerator, which means that at equilibrium, this reaction favors the reactants. Okay, sometimes you might say the left-hand side and refer to it as left and right. So this reaction favors the reactants. At equilibrium, I expect to have a higher concentration of NoCl than I do of No or Cl2. So if we want to do this type of problem, and when I say this type of problem, what do I mean? I mean this problem down here. If we start with 1 molar NoCl in a sealed flask, and there's no No or Cl2, determine the equilibrium concentration of all species. Now often these questions will not actually have this part. It'll just say start with 1 molar NaCl in a sealed flask. If they don't tell you anything about the concentration of the products, you can assume that there are no products involved. Okay. In this kind of situation, I normally start by rewriting my equation at the top of my paper. All right, and then I'll make these columns. ICE, okay? ICE stands for initial. So in this place is where we'd want to put the initial concentrations. Now a common thing here, you need to either be using concentrations or pressures. You can't use absolute number of moles. Okay, so in this case, we've got 1.0 molar to start with, and we've got 0 and 0 over on this side. Next is what's called change. This is when we look at how the reaction will now shift. So in this case, we are going to use the stoichiometric quantities, and we're going to use some logic to figure out what we put in change. So what I know is that every time 2 molecules of NoCl disappear, I get 2 NOs and 1 Cl2. Now I don't know how many NaOCls are appearing at any or disappearing at any given time, but I know that the ratio of disappearance to appearance is always going to be 2 to 2 to 1. So I'm going to put here negative 2x. What does that mean? It means that I'm going to be losing concentration of NoCl, and this could be happening 2 times the rate of, for example, appearance of Cl2. On this side, I've got plus 2x, right? Now I'm going to be making products, and again, this ratio, it's going to be 2 times the amount of Cl2 that I'm making. Okay, so I'm going to use these algebraic quantities to express the ratio with which reactant products are formed. And then my equilibrium, I'm going to have concentrations of 1 minus 2x. I'm going to have concentration of 2x, and I'm going to have a concentration of x at equilibrium. So this is where my K comes in. 1.6 times 10 to the negative sixth is going to equal, and I'm going to use my expression up here. So the concentration of NO squared times the concentration of Cl2 over the concentration of NoCl squared. Okay, and now I have to solve for this. What I see is that I have a potential quadratic situation. If you want to solve the quadratic, you can, and in some cases you have to. I will use, if I'm just doing homework, I will use Wolfram Alpha because it's just really easy. You may also have a calculation, something on your calculator that will allow you to do this. But what I would say is I would be checking to see if I can use an approximation that we often use in equilibrium, which is X small? And when I say small, I mean compared to starting concentrations. So I'm essentially asking, is X small compared to 1 molar? Because that's our only starting concentration. How do I figure that out? Well, I'm looking at K. Okay, in this case, K is very small. Whoops, sorry, it's not, there you go. K is very small. It's 1.6 times 10 to the negative 6th. And what that means is that probably we're not going to shift a whole lot away from our reactants, right? Minus 2x, when I subtract that x, it's probably not going to create a whole lot of products because I know that the ultimate ratio of reactants to products is quite small, 1.6 times 10 to the negative 6th. So I'm actually going to do this approximation. Is x small compared to the starting concentration? I'm looking at K and I'm saying, in this case, yes. Okay, yes, X is small, compared to the starting concentrations. And what that means is I'm going to rewrite this expression. I'm going to say anytime I'm adding or subtracting X, it's negligible. So 1.6 times 10 to the negative 6th equals, and I can rewrite this as, I'm going to rewrite the top as 4x cubed. Okay, that's just algebra. I'm not actually making any approximations there. But I'm going to say that essentially that 2x that I was going to subtract is so small that I don't care. Since x is small, I've omitted the subtracted term. Okay. You could also do that with an additive term if, for example, one of those appeared up there. And then I'm going to solve this equation, and I'm going to get, I think, x equals, where did I write this down? X equals 0.0074 molar. But my problem isn't done. I'm looking for the equilibrium concentrations of all species. So what that means, X, remember, is actually going to be the equilibrium concentration of Cl2, because it says so right there. 2X will be the concentration of NO. That ends up being 0.015 molar. And my concentration of NaCl at equilibrium is going to be 1 molar minus 2 times X, which is going to end up being 0.99 molar. Anytime you make this approximation that X is small, it's good practice to kind of go back and look at what you solved for and whether it was a good approximation. Here, right, you see that instead of using 1 in the bottom, our real equilibrium concentration of NaCl was 0.99. The difference between 1 and 0.99 is 0.01. So there's only a 1% difference between the value that we did use and the value that we obtained as the equilibrium concentration. That 1% difference means that this was a fine approximation to make. Generally, you don't want to see greater than 5%. Okay. If your NaCl concentration at equilibrium ended up being more than 5% away from the value that you ended up using in the equilibrium expression, then you need to go back and use the quadratic equation. All right. Last but not least, so in this situation, it was pretty obvious what the sign had to be. We had negative 2x plus 2xx. How did we know? Because we had starting concentration of reactant and we had no products. So it was clear that the reaction had to shift from the left to the right, even though not very much. So what happens if you have starting concentrations of all the compounds? What if it's not really clear by inspection which way the reaction has to shift to achieve equilibrium? That's when we're going to use something called Q, which is called the reaction quotient. Okay, and it's going to tell you when you compare this to K, this is going to tell you which way the reaction shift. Okay. So for our equation on the other side, actually our Q is going to equal the same. It's going to have the same expression as our equilibrium expression. The only difference is that here, for Q, the concentrations can be any concentrations. Whereas for K, those concentrations have to be equilibrium concentrations. Okay, so when we compare Q to K, it'll tell us which way it has to shift. How? Well, let's see. Here's a problem of the type that you might see if they're asking you about Q. So at 100 degrees Celsius, the equilibrium constant for the reaction COCl2 goes to CO, and Cl2 has the value K equals 2.19 times 10 to the negative 10th. Are the following mixtures at equilibrium? And if not, indicate the direction the reaction must proceed to achieve equilibrium. Okay, so in this case, our value of Q, we're going to write it out just as we would for K. We've got our products over our reactants raised to the correct coefficients. Okay, so if I substitute all this in, so I substitute these concentrations into the Q expression, I get a value of 1.09 times 10 to the negative 8th. And I compare that to K. Okay, this value is greater than the value of K, 2.19 times 10 to the negative 10th. What does this mean? This means that this mixture, the current mixture that we have, has a greater concentration of products than I expect to see at equilibrium. What that means is that the reaction has to shift, making reacting products and going backwards towards reactants. Okay, so we're going to need to shift this equilibrium toward the reactant side. And so what that means is if I was setting up an ice problem, and I'm not actually going to do this out, but if I was setting up an ice problem, I would expect in the change column to see negatives on this side and positives on this side, because I will be shifting left towards the reactants. Okay, so when Q is greater than K, I'm going to shift left. Now in the second situation, my Q is 5.5 times 10 to the negative 12th. In this case, this is less than K, 2.19 times 10 to the negative 10th. So we have the opposite situation here, where we have too many reactants, and we need to shift towards products. So this reaction is going to shift to the right, which again in an ice problem is going to look like negative signs on the reactant side and positive signs on the product side.